So today we're going to be doing chapter 5. So we did chapter 2, 4, now we're doing 5. And next week we'll have an exam on chapters 2, 4, and 5. So today we're going to go through the PowerPoint real quick. You guys have the study sheets as usual. Take the quiz when you're done. And next week we'll have the exam open from Monday until Sunday night. Any questions, shoot them over to me via email. So let's get started going through the PowerPoint for chapter 5. And then as usual, we have the study sheet for chapter 5 that's pretty much summing up the PowerPoint in my view, an easier to understand way. So chapter 5 talks about image reconstruction. So what is image reconstruction? Basically the attenuation data that's collected from the detectors, right? The X-ray beam hits the detectors, that data, okay, requires mathematical algorithms to build the CT image for us to view, okay? So there's basic algorithms required, and there's 3 concepts that we can look at for those algorithms: Fourier transform, convolution, and interpolation. Okay, so what's an algorithm? An algorithm is a set of rules or directions for getting a specific output from a specific input. So you put an input, and then there's the rules that go in and adjust that input to give you a specific output. All vagueness must be eliminated. It has to be strictly mathematical, very predictable. The rules must describe operations that are so simple and well-defined they can be operated by the machine. And it must terminate by a finite number of steps. So you want to know these things about algorithms. Just know that an algorithm is a set of directions to give you a specific output from a specific input. No vagueness. It has to be simple, and it must terminate after a finite number of steps. So let's talk about those concepts. A Fourier transform is a tool used to reconstruct images for a patient's anatomy in CT and MRI. It's mainly used in MRI. You really don't need to know much about Fourier transform except that it divides a signal waveform into a series of differential sequences and amplitudes which make reconstruction of a CT image possible. That's not it, actually. This one. This is all you need to know about Fourier transform. It's a mathematical function that converts a signal in the spatial domain to a signal in the frequency domain. This is literally all you gotta know. We're gonna talk about Fourier transform a couple more times. Just know this, and you don't really need to know much else. Just know those 2 things, this one thing. Convolution, convolution, filter, convolution, filter, convolution, filter. Anytime you hear convolution, just think filter. Convolution is a digital image processing technique to modify images through a filter function. That's all convolution is. It's basically just adding a filter, okay? Interpolation is a mathematical technique to estimate. Interpolation, estimate, okay? So interpolation gives you the ability to estimate the values of function from known values on either side of the function. So in CT, we don't technically scan every single part of the body, okay? We scan certain slices, and because the patient's moving, there are areas that are going to be missed, right? It's going to be a very small area. So if you've done a CT, then you know that we do, for example, 5 millimeter slices every. If we do every 5 millimeters or whatever, then you're perfectly overlapping. But even then, because the patient is constantly moving while it's scanning, there's going to be some spaces, and we'll talk about interpolation some more, but basically we estimate the values in those spaces. We estimate. That's why if you do like axial scanning, where it's step and shoot, it scans and then stops and then it moves the patient scan, that's more accurate than helical, even though it's not really efficient, but it's more accurate because there's no estimation. We're scanning every single part of the body. But when the patient's constantly moving while we're scanning them, there is stuff that's going to be missed, and that's what interpolation does. It'll estimate the stuff that we missed based on the stuff that we didn't miss. So image reconstruction from projections, you just need to know what array sum, and a projection are. Just memorize those terms. Reconstruction algorithms. Okay, so here's the meat of it. There's a couple different reconstruction algorithms: back projection, iterative algorithms, and then filter, back projection, and Fourier reconstruction. So back projection. Back projection is basically the summary of multiple projections to produce an image. So back projection is where you take a bunch of images, you put them together, and then you have a new image. Okay, it does not produce a sharp image of the object, and it's not used in CT for that reason. Okay, it's characterized by a star pattern artifact. So if you look at this image here, we put a bunch of images together, and we got that reconstructed image. And so you want to know about back projection, that it's a summary of multiple projections to produce an image, and you also want to know that it's characterized by star pattern artifact. Iterative algorithms, this can get a little complex, but basically you just need to know this first paragraph. It starts with an assumption and compares the assumption with measured values. Then it makes corrections to bring the two into agreement, okay? And then it keeps repeating back and forth until the measured values are within acceptable limits. So it starts with an assumption. So let's say I assume that you're thinking of the number 10, okay? Then I assume that you know, this patient weighs 200 pounds, okay? And then we measure the patient, and they weigh 220. So then I make another assumption to get it a little closer, and I'm like, okay, well, because I don't know that they're 220, I'm thinking maybe they're 210. So you keep going until it gets within limits where I'm like, okay, he's 218 and he's actually 220, and that's fine because we're within the limit. It's kind of a weird example, but that's basically what it does. It's also not really used in CT because there's several limitations, so it's not used in commercial scanners. Originally, maybe used now, but you just need to know this paragraph about iterative algorithms. So what do we use? We talk about back projection, we talked about iterative algorithms. What's used mainly is filtered back projection. Not back projection, filtered back projection. It's also known as the convolution method. What does convolution mean? Remember we said convolution means filter, right? So filtered back projection is also known as a convolution method. It's commonly used in CT systems today, and the common problems found in this are noise and streak artifact, but it solves for that star pattern thing that we talked about in the beginning. So back projection versus filtered back projection. This is a quick image that shows you that. So in filtered back projection, you don't have as much, let's see here what it says. So back projection results in an unsharp image. Filtered back projection uses digital filter, a convolution filter, to remove the blurring, which produces a sharper image. So at the top, you have the back projection, and at the bottom, you have the digital filter that gives you the sharper image. Just know that the filtered back projection is better because it uses a filter, and you get less blurring, sharper image. For your transform, or for your reconstruction, again, we don't use, just know that it's mainly used in MRI, and it does that thing from the spatial domain to the frequency domain or whatever. There's an example of that. Skip over that. Chrome beam algorithms for multi-slice. So remember we said in multi-slice CT, we went from like pencil beam to fan beam, and then when we got multiple detectors, we got into cone beam, okay? So cone beam occurs when there's the beam diverges along the axis of the patient and when you have multiple detectors. You guys can read through this, pretty straightforward stuff you got to memorize. Same thing with three-dimensional. So let's talk about types of data. We have measurement data, raw data, convolved data, and image data. Okay? So measurement data is also referred to as scan data. This data comes straight from the detectors. Okay? This data needs to be pre-processed, okay, before reconstruction algorithms can be applied. So that's measurement data. Raw data is this data when it's pre-processed, and it's stored and can be used as needed. So when you take a scan, there's measurement data that's not really usable. Once that data is pre-processed, it becomes the raw data that we know, and you can use it later on. Convolved data is the data that goes through the convolution technique. Convolution is applying the mathematical filter kernel to the kernel to the raw data. Or we said convolution, convolved always talks about filters. So we said measurement data comes straight from the detector. Once it's pre-processed, it becomes raw data. Once the raw data, okay, once a filter or a kernel is applied to the raw data, it becomes convolved data. And basically what that does is it removes blurring and it improves image quality. And once this data is reconstructed, it becomes image data. So image data is convolved data that has been back projected into the image matrix to create CT images displayed on the monitor. And is that it? Yep, that's pretty much it. All right, so go ahead, take the quiz on this, and then next week be ready for the exam. Let me know if you guys have any questions at all. This study sheet here should do